Welcome to the first example in the chapter of strain. The question reads, the force applied to the handle of the rigid lever arm causes the arm to rotate clockwise through an angle of 3 degrees about pin A. Determine the average normal strain developed in the wire. Originally, the wire was unstretched. Okay, so we are immediately given that the basically the change in angle relative to A, when this bar or when this guy pushes or pulls this bar down, it will rotate clockwise 3 degrees relative to A, so we're just going to call this theta, right? So that's our first value that we're given. So theta is equal to 3 degrees about pin or point A, so about A. What other notes are we given in this question? Well, we are given that this bar is rigid, and that is very important because it's basically an assumption that we have. Because if it's not rigid, it may, we don't know if it's going to bend, and that will change it will significantly change the strain in this wire. Well, not significantly, but it will have some effect if this deforms in any way. So what we're going to say is this bar is rigid. So when it does rotate, this is a huge exaggeration, but when it does rotate these 3 degrees, this bar is going to be completely straight, right? No deformation whatsoever, for at least our calculations. So that is what we're going to say. We're going to say bar AB is rigid. Okay, we're trying to find strain in this question, so let me actually go to unknowns. This question wants us to find strain in the wire, and I think, or it is the first time, so strain in wire. It's the first time we're dealing with strain, so the equation for strain is equal to the change in length divided by the original length, okay? So, for example, in this wire, if it extends an extra, 50 millimeters, probably isn't, it's not 50 millimeters, but if it does, this is our delta L, this is our L naught, so therefore delta L, so the change in length is just equal to the new length minus the original length, okay? Perfect. I think that's all we need for givens, but actually there is one formula that, it's a spoiler for later on, but in this question we're going to use law of cosines, and that is basically c squared is equal to a squared plus b squared minus 2ab cosine of the angle C. And in a triangle representation, that does not look like that. It looks like this. If this is B, this is B as well. This is A, this is A, this is C, this is C. Okay, perfect. So we can move on to basically what we want to do in this question is we want to find strain as a summary. This is the game plan, right? Okay, so we want to find strain. How are we going to find strain? Do we have L naught for the wire? Do we have the original length? Well, yeah, we do. It's 600 millimeters, right? 600 millimeters. Okay. Can I find delta L? All I need to do is find delta L. What is delta L equal to? Well, it's equal to the original length, which I said we have, but it's equal to the new length minus the original length. We have the original length, we want to find the new length. How can I find the new length? Well, let's first draw it out, because it's very important to draw things out so you understand yourself. So it's not really enough free body diagram, but actually let's just call it diagram, so to not confuse anybody. Diagram. So I'm just going to see a before and after. I'm going to draw it myself, right? So if this is the bar, and this is point B, this is point C, this is A, and then let's say D is up here, right? We have our wire going down from D to B. Right here is 45 degrees, as seen in the problem. And then again, we have our force going down at C, or force of pulling, right? We're not really going to put down the pin connection because it doesn't really matter, as you'll see in just a second. This, like that, this is 90 degrees. Okay. And this distance right here is 0.6 meters. I converted from millimeters to meters. Can I find this distance right here? Well, yeah, sure. This is just cosine of 45, right? It's just 0.6 cosine of 45. can I find this distance right here? Yep, it's 0.6 sine of 45, right? I'm going to write that down. This distance on the right is 0.6 sine 45, 0.6 cosine 45, right? I think that's a pretty good accurate representation of this drawing. Now let's see what happens after, okay? And let's make this a bit smaller. What happens after is that we still have our point A. Actually, let's actually copy this. Let's draw above it. Technology is very, very cool. Okay, anyway, so this guy rotates after this force is applied. Remember, it's a rigid bar, so we don't have any deformation within the bar, right? It's not bending or anything like that. Let's say our force still acts like this. This point right here now, let me pick a nice bright color. Let's do orange. This point right here now is C prime, right? This point over here, let's say, for example, is B prime. And then A is the exact same. And this, it's an exaggeration, but it's 3 degrees. Right? Okay. Where's the wire? The wire is going from D. It's still going from D. And it's going to B. Right? Let me pick a thicker color. That's not straight. Perfect. I think that's a beautiful, very messy, but hopefully you get the idea. This is our new kind of structure. Right? Once you apply this force right here. You have B prime, you have C prime, you have your original point A, and you have your D. My question to you now is, has this distance changed? The correct answer is no. Okay. Has this distance changed from here to here? Has it changed? Well, no, our bar is rigid, right? It may not look like it may not be to scale, but when I push this bar down, this distance from here to here is the exact same as from here to here. The wire may have changed length, but the distance is the exact same. So, in fact, this, I'm running out of colors. Oh, this is a nice color. Wow. Okay, this one right here is still 0.6 cosine of 45, right? And this one right here is still 0.6 sine of 45, correct? This is my new length L that I want to find. This right here is my new length L that I want to find delta L, correct? Okay. This is where cosine law comes in. Cosine law allows us to find a length if we translate this triangle into this diagram, and let's just use this beautiful red color. This is C, right? This is B, this is A, and this is the angle C, right? If we translate it to this formula, we have all the values to find this guy right here. And you may ask, what's C? Well, it's just our original 90 plus the extra 3 degrees of variation, or of, variation. Hopefully that makes sense. Okay, so from this mess, we are going to find that we can use cosine law. Okay? So, and I really hope that was understood. But hopefully, or I will go through it quickly once again. So cosine law to find L. Okay. We're not going to call it L. Actually, we will call it L. Remember, this is the formula, so I'm going to refer to this. C squared. What's our C squared? Well, that's L squared. Okay. What do we say our A is? We will pick this one to be A. Doesn't really matter. This is going to be A. This is going to be B, C, and then this, I don't want to further mess it up, but this inner angle is C. Okay. So this is A squared, so 0.6 sine of 45 squared plus 0.6 cosine of 45 squared minus 2 times 0.6. Should I just wrote? Never mind. What is it? A? What did we say? It was sine 45 times 0.6 cosine of 45 times cosine of the angle C. What is the angle C? Again, it's this inner angle. What is this inner angle? It's 90 plus 3. So 93. If you do this absolutely beautiful calculation, you're going to get that L is equal to 0.6155 meters. So your new length after you rotate it relative to A 3 degrees, your new length of the wire is around 615 degrees or 615 millimeters. But we will get that in just a second. Perfect. We go back to givens, right? We want to find strain. We want to find delta L. Did we find delta L? Not yet. Delta L is equal to L, which we just found, minus the original length. Okay, do we have the original length? Yes, we do. This is a very trivial calculation. It's 15 millimeters divided by original length. Basically, 6 millimeters or 600 millimeters, and we will do that right now. And then we have our final answer. Solve for strain. Okay, strain of the wire BD. Let me zoom in so my handwriting is not a mess. Strain of the wire BD is equal to delta L over L naught. This is equal to L minus L naught over L naught. This is equal to 0.6155 meters minus 0.6 meters divided by 0.6 meters, and what you're going to get from this is 0.0258. If you convert, it's a unitless dimension, but if you want to convert, it is 0.0258 millimeters over millimeters, and this is your final answer. This is the strain of the wire BD.